Hi, Ananya. Can you hear me okay?
Yes, loud and clear. Can you hear me all right?
Perfectly, thanks. And thanks for making the time today.
No problem at all. Happy to be here.
So this will be mostly technical, about 45 minutes or so. Sound good?
Sounds good. Let's do it.
Great. To start, could you introduce yourself?
Sure. I'm Ananya, and I've been doing backend work for about 6 years now. My stack is mostly node.js and Express, a bit of nest.js, with PostgreSQL and MongoDB, plus Redis and Kafka or RabbitMQ for messaging, and Docker and AWS for deployment. These days, I also lead and mentor a small team of 3. I'm looking for a role with more ownership of system design and architecture.
Nice. Tell me about your current project.
I own the backend for a logistics and delivery tracking platform. The core job is ingesting real-time GPS pings from vehicles, running them through a queue-based pipeline, and pushing live updates to dispatchers and customers. It's a set of microservices behind an API gateway. We handle tens of thousands of vehicles and a few thousand events a second at peak.
So, you own the real-time ingestion side.
Yeah. A device hits the ingest endpoint, the event goes onto a queue, a pool of workers validates and stores it, and then we push the position out to clients over WebSockets. The queue is what keeps a traffic spike from knocking the database over.
Great. Let's start with some fundamentals and go deeper from there.
Sounds good.
What's a closure and where have you actually used one?
A closure is a function that keeps a reference to variables from the scope it was created in, even after that outer function has returned. I use it for middleware factories, a function that takes config, like a required role, and returns the actual Express middleware that closes over that config. Same idea for per request rate limiters.
Good. Hoisting. And the temporal deck zone, var versus let versus const.
Var declarations are hoisted and initialized to undefined, so you can reference one before its line. Let and const are hoisted too, but not initialized, referencing them before the declaration throws, and that gap is the temporal dead zone. Var is function scoped, let and const are block scoped, and const just means the binding can't be reassigned.
Right. How does this binding work and how do arrow functions change it?
For a normal function, this is set by how it's called, the object before the dot, or undefined in strict mode if you call it bare. Arrow functions don't have their own this. They capture it lexically from where they're defined. That's why you use an arrow for a callback inside a class method instead of bind.
Okay. Walk me through the event loop.
Lib of runs phases in a loop, timers for do set timeout callbacks, pending callbacks, then poll where most I/O completions run, then check for set immediate, then close callbacks. Between every phase it drains the microtask queue, resolved promises and processed at next tick, so microtasks always run before the next macro phase. Does that make sense?
It does. Process.next tick versus set immediate.
Process next tick runs before the event loop continues, right after the current operation, ahead of any promises even. Set immediate runs in the check phase, on the next loop iteration. So next tick is more immediate, but if you recurse on it you can starve the loop, which is why set immediate is usually the safer choice.
People say Node is single-threaded. What does that actually mean?
Your JavaScript runs on one thread, the event loop, so two pieces of your code never run in parallel. But Node isn't only that one thread. libov has a thread pool underneath for things like file system calls, DNS, and crypto, and the OS handles network I/O. So I/O is concurrent. It's the JavaScript execution that's serialized.
And if you block the event loop, how do you avoid that?
If you do something CPU-heavy synchronously, a big loop parsing a huge payload, a slow crypto call, the whole process stalls, and every request waits. So you don't do that on the main thread. Offload CPU work to worker_threads, or split it into chunks, or push it to a separate service. Cluster and child_process are for running multiple processes, not for unblocking one.
Good. Callbacks to promises, to async await, and error handling along the way?
Callbacks gave you nesting and error first arguments. Promises flatten that into then and catch. Async/await lets you write it like synchronous code. With await, you wrap it in try/catch, or the rejection bubbles up. Promised all rejects as soon as one fails. Promise all settled waits for all and reports each. And an unhandled rejection will crash the process, so you catch it.
Right. Streams. And what's back pressure?
Streams let you process data in chunks instead of loading it all into memory, reading a big file, a large HTTP response. Back pressure is when the consumer is slower than the producer. The writable side's buffer fills, write returns false, and a well-behaved pipeline pauses the source until it drains. Stream.pipeline wires that up for you and propagates errors and clean up properly.
When do you reach for a buffer?
When I'm dealing with raw binary file contents, an image, a network packet, hashing, or encryption, anything that isn't text. A buffer is a fixed-length chunk of bytes outside the V8 heap. For text, I decode it to string with an encoding. For binary, I leave it as a buffer.
An event emitter. What's that Max listeners warning about?
Event emitter is the pub/sub building block. On to subscribe, emit to fire. Node warns when one emitter has more than 10 listeners for an event, because that usually means you're adding listeners in a loop or per request and never removing them, which is a memory leak. The fix is removing them on cleanup, not just bumping the limit.
Okay, let's move on to Express and API design. How does middleware ordering work? And what's the error handling middleware signature?
Middleware runs in the order you register it, each one calling next to pass control on. So body parsing and auth go before the routes that need them. Error handlers are special. They take 4 arguments: error, request, response, next, and express only routes to them when something passes an error to next or throws. You put them last.
How do async errors propagate in Express?
In Express 4, a rejected promise inside an async handler isn't caught automatically. You have to call next with the error, or wrap every handler in a helper that does a catch and forwards it. The Express async errors package patches that globally. Express 5 fixes it. A rejected async handler goes to your error middleware on its own.
Good. Talk me through REST design, resources, verbs, status codes.
Resources are nouns, /orders, /orders/123, and the HTTP verb is the action. Get to read, post to create, put or patch to update, delete to remove. Status codes carry meaning: 201 for a created resource, 204 for success with no body, 400 for malformed input, 422 for valid shape but bad values, 409 for a conflict, 429 for rate limited.
Idempotency. And how would you make a create payment endpoint idempotent?
Idempotent means running it twice has the same effect as running it once. Get, put, and delete are. Post isn't by default. For create payment, the client sends an idempotency key in a header. We store it the first time we process and save the result against that key. If the same key comes again, we just return the saved result instead of charging again.
Pagination, offset versus cursor.
Offset is limit and offset. Simple, lets you jump to a page, but it gets slow on deep pages and rows shift if data changes underneath you. Cursor pagination passes an opaque pointer, usually the last item's sorted key, and asks for the next batch after it. It's stable and fast at scale, but you can't jump to an arbitrary page. I default to cursor for big feeds.
How do you handle API versioning?
Usually a version in the path, /v1/v2, because it's explicit and easy to route and cache. Some teams use a header or an accept media type instead, cleaner in theory but harder to test by hand. Whichever you pick, the rule is don't break v1 while v2 exists. Additive changes are free. Removals need a new version.
Input validation.
Validate at the boundary, the moment a request comes in, before any logic touches it. I define a schema with Zod or Joy for the body, params, and query, reject anything that doesn't match with a 400 and a clear message, and pass the parsed, typed object downstream. Never trust the client. Database constraints are a backstop. not the first line of defense.
GraphQL, the n+1 problem, and when would you pick it over REST?
With GraphQL, resolving a list and then a field on each item naively fires one query per item, the n+1. Data loader fixes it by batching those lookups into one query per tick and caching within the request. I'd pick GraphQL when clients need very different shapes of data and you want to avoid endpoint sprawl. REST is fine and simpler for a straightforward CRUD API.
Rate limiting, how do you implement it?
Token bucket or sliding window with the counters in Redis, so it works across all your instances. Each key, per user when they're authenticated per IP otherwise, gets a budget that refills over time. The update has to be atomic, so I do it in a small Lua script. When they're over the limit, return 429 with a retry after header, so clients back off cleanly.
Okay, auth and security now. Walk me through a JWT.
It's 3 base 64 parts: header, payload, signature, separated by dots. The header names the algorithm, the payload has claims like user ID and expiry, and the signature is those two signed with a secret or a private key. HS256 uses one shared secret, RS256 signs with a private key, and anyone verifies with the public one. Put an ID and roles in it, never a password, and keep the expiry short, because it's stateless and hard to revoke.
Light. So, refresh tokens.
Access tokens are short-lived. The refresh token is long-lived and used only to get a new access token. I store it in an HTTP-only cookie, not local storage, so script can't read it, and I rotate it on every use, issue a new one, invalidate the old. If a rotated token gets reused, that's a theft signal, and I kill the whole session. The refresh tokens live server-side, so I can revoke them.
Sessions versus tokens. Quick take. Quick take.
Sessions keep the state on the server with a session ID and a cookie. Easy to revoke instantly, but you need shared session storage across instances. Tokens are self-contained, so any instance can verify without a lookup, which scales nicely, but revocation is awkward. In practice, I do short-lived tokens plus server-side refresh tokens to get most of both.
OAuth and OpenID Connect, the authorization code flow, and why PKCE?
The app sends the user to the provider. The user logs in and consents. The provider redirects back with a short code. The app exchanges that code, plus its client secret, for tokens on the back channel. OpenID Connect adds an ID token so you get identity, not just access. PKC is for clients that can't keep a secret, like a mobile app or SPA. They send a hashed verifier up front and the real one at exchange, so a stolen code is useless.
Password storage.
Never plain text, never a fast hash. Use BCRYPT or Argon 2. They're deliberately slow and salt each password, so identical passwords hash differently and rainbow tables don't help. For a reset, you email a single-use, time-limited token, store only its hash, and when they use it you let them set a new password and invalidate the token.
CORs and the pre-flight request. What's going on there?
CLRS is the browser's rule that a page on one origin can't read a response from another origin unless the server opts in with the right headers. For anything beyond a simple request, a custom header, a put, a JSON body, the browser first sends an options pre-flight asking what's allowed. If the server's answer covers it, the real request goes. It's a browser thing. Server-to-server calls don't care.
Common vulns you watch for.
SQL injection, always parameterized queries, never string concatenation. Same idea for NoSQL, where a crafted object can change a query. CSRF, same site cookies and tokens for state-changing requests. SSRF, validate and allow list any URL the server fetches. Rate limit login and reset endpoints and keep secrets in a vault or environment config, not in the repo.
Good. Databases now. SQL versus NoSQL, the trade-offs.
SQL gives you a fixed schema, joins, and real transactions, great when relationships and consistency matter, which is most business data. NoSQL, like a document store, is flexible schema and scales horizontally easily. good for huge volume or data that's naturally one big document. I default to PostgreSQL and reach for Mongo when the access pattern really fits documents.
Indexing. When, what kind, and the cost.
You index columns you filter, join, or sort on a lot. The default is a B tree, which handles equality and ranges. A compound index has a left prefix rule. An index on A, B helps queries on A or A and B not be alone. A covering index includes every column the query needs, so it never touches the table. The cost is slower writes and more storage, so you don't index everything, and you check the query plan with explain analyze.
The n+1 query problem in a database context.
You fetch a list of orders, then loop and run one query per order for its items. That's n+1 round trips. The fix is to fetch them together. A join, or a single where-in query for all the IDs, or your ORM's eager loading. One query instead of 100. It's the single most common reason an endpoint is mysteriously slow.
Transactions, ACI seed and the isolation levels.
ACID is atomic, consistent, isolated, durable, all or nothing, valid state. Transactions don't step on each other. Committed data survives. Isolation levels trade strictness for speed. Read committed stops dirty reads. Repeatable read also stops a row changing under you. Serializable behaves as if transactions ran one at a time, preventing phantoms too. Postgres defaults to read committed.
When do you actually need a transaction?
When several writes must all succeed or all fail together. The classic transfer money between two accounts, or create an order, decrement inventory, and write a ledger row. If a partial state would be wrong or hard to clean up, wrap it. For a single row update, you don't need one. That's already atomic.
And across services. Distributed transactions, the saga pattern.
You can't run one transaction across services, so a saga breaks it into a sequence of local transactions, each publishing an event that triggers the next, with a compensating action to undo a step if a later one fails. Two-phase commit gives stronger guarantees, but it's rare. It needs everyone to cooperate and a coordinator that, if it dies mid-commit, blocks everything. Sagas trade that for eventual consistency.
Connection pooling, why, and how do you size it?
Opening a database connection is expensive, so you keep a pool of warm ones and hand them out per query.
Normalization versus denormalizing for reads.
Normalization keeps each fact in one place. No duplication, easy correct writes, but read-heavy pages need lots of joins. Denormalizing copies or precomputes data, so a hot read is one cheap lookup, at the cost of keeping the copies in sync. I normalize by default and denormalize specific hot paths once the join actually shows up as a problem.
MongoDB, embedding versus referencing, and shard key choice.
Embed when the child data is owned by the parent and read together, an order and its line items, so it's one read. Reference when it's shared, grows unbounded, or is queried on its own. The aggregation pipeline is stages: match, group, lookup, sort, for transforming data server-side. The shard key has to spread writes evenly and match your common queries. A monotonically increasing key like a timestamp is bad. It hotspots one shard.
Zero downtime migrations. How?
Expand and contract. First expand, add the new column or table, deploy code that writes to both old and new, backfill the existing rows in batches. Then switch reads to the new shape and verify. Then contract. Once nothing reads the old one, drop it. There's no single deploy where the schema and the running code disagree, and you avoid long table locks.
Good. Catching and scaling. Redis, what do you use it for, and how do you write through it?
Redis for sessions, rate limit counters, hot lookups, leaderboards, sometimes a job queue. All with TTLs. The usual pattern is cache aside. Check Redis. On a miss, read the database. Populate the cache, return. Write through writes cache and database together so they stay consistent. Right behind writes cache now and the database async. Faster but riskier. And on an update, I invalidate or rewrite the key. Stale cache is the classic bug.
Cache stampede, the thundering herd. How do you handle it?
A popular key expires, and suddenly every request misses at once and slams the database. A few defenses. A short lock so only one request rebuilds it while the others wait or serve stale. Jittering the TTLs so keys don't all expire together, or stale while revalidate. Serve the slightly old value and refresh in the background. I usually do the lock plus TTL jitter.
What are the caching layers? Top to bottom?
A CDN at the edge for static assets and cacheable responses. HTTP caching with cache control headers and e-tags, so the browser and proxies reuse responses. An application cache like Redis for computed data and query results, and the database's own buffer cache. You want to catch a request as high up that stack as you can.
Memory leaks in Node. Causes, and how do you find one?
Usual culprits: a closure or a module-level array holding references that never get released, an unbounded map or cache that only ever grows, listeners or timers added per request and never cleared. To find it, take heap snapshots over time as memory grows and diff them. The constructor whose retained size keeps climbing is your leak. Clinic.js and the inspector make that easier.
And CPU profiling?
Run with prof to get a V8 profile, or use Clinic Flame or 0x for a flame graph. The widest frames are where the time goes. I also watch event loop lag as a metric. If it climbs, something synchronous is hogging the thread. And profile under realistic load, not on an idle box.
How do you scale a node service?
Keep it stateless so any instance can serve any request, sessions, and cache in Redis, not in process memory. Then run many processes behind a load balancer, the cluster module, or PM2 across cores per box. Avoid sticky sessions by using shared state. And do a graceful shutdown on SIGDERM. Stop accepting new connections, finish the in-flight ones, close the database pool, then exit, so a deploy doesn't drop requests.
How would you scale this to 1 lakh concurrent users?
Load balancer in front, horizontally scale the stateless app tier. Read replicas for the database and aggressive caching, so most reads never hit the primary. Push heavy or slow work onto a queue and process it async cap connections per instance. Add circuit breakers around downstreams, so one slow dependency doesn't cascade, and a CDN for everything static. Then load test it and find the real bottleneck rather than guessing.
Good. Messaging and distributed systems. When do you reach for a queue?
When work can be done asynchronously, when you want to absorb spikes, or when you want to decouple a producer from a slow or flaky consumer. In our system, the GPS ingest just drops events on a queue and returns immediately. The workers chew through them at their own pace. It also lets you retry failures without blocking the caller.
RabbitMQ versus Kafka versus SexUS. High level?
RabbitMQ is a traditional message broker, flexible routing, good for task queues. Messages go away once acknowledged. Kafka is a distributed log, high throughput. Messages are retained and replayable, great for event streams and multiple independent consumers. SQS is the managed AWS queue, dead simple, no ops, less control. I'd pick Kafka for the GPS stream, RabbitMQ, or SQS for plain job queues.
At least once delivery. What does the consumer side need?
If delivery is at least once, you will see duplicates, so consumers have to be idempotent, key off a message ID and skip one you've already processed. Messages that keep failing go to a dead letter queue after some retries so they don't block the line, and you alert on it. If you need ordering, you partition by a key so related messages land on the same consumer in order.
Pub sub versus a work queue.
A work queue. Each message goes to exactly one worker. You're distributing tasks. Pub/sub. Each message is broadcast to every subscriber. You're notifying many independent consumers, like several services reacting to an order-placed event. Different shapes. Competing consumers versus fan-out.
Eventer consistency. What does it mean and when is it acceptable?
It means after a write, replicas or downstream services converge to the new value, but not instantly. there's a window where a reader might see the old one. It's fine for things like a notification count, a search index, and analytics dashboard. It's not fine where a stale read causes a wrong decision, like an account balance right before a withdrawal.
Microservices versus a monolith. When do you split?
A monolith is simpler, one deploy, easy transactions, no network between modules, and it's the right start for most things. You split when teams are stepping on each other, when parts have very different scaling or reliability needs, or a piece needs its own release cadence. The cost is real: network failures, distributed transactions, more operational surface. So split deliberately, not by default.
The dual write problem. One sentence.
If you write to the database and then publish an event as two separate steps, one can succeed and the other fail, and now you're inconsistent. The transactional outbox fixes it by writing the event into a table in the same transaction and having a separate process relay it.
Okay, a few scenarios. An API endpoint is suddenly slow in production. How do you debug it?
Start at the dashboards, latency, error rate, throughput to confirm and scope it. Pull traces for that endpoint and see where the time goes. Database query times, external API calls, time in our own code, event loop lag. Check whether it lines up with a recent deploy or a traffic change. Basically narrow it down layer by layer until one thing stands out.
Say you've checked all that and the query is already optimized. Now what?
Then I look past the query. Connection pool exhaustion, so requests are queuing for a connection. Garbage collection pauses, a slow downstream service it depends on. Lock contention on a hot row. I'd also check whether it's the average that's bad or just P99. A few slow outliers reads very differently, and whether there's a hot loop burning CPU around the call.
Design a rate limiter for our public API.
Token bucket in Redis, 1 bucket per API key. Each key has a capacity and a refill rate. On a request, an atomic Lua script refills based on elapsed time, checks for a token, decrements if there's one. Over the limit, return 429 with X rate limit remaining and retry after headers. The Lua script keeps it atomic across instances, and the keys expire on their own when idle.
Last scenario, the server runs out of memory and crashes every few days. How do you find it?
It's a slow leak, so I take heap snapshots at intervals as memory climbs, say a few hours apart, and diff them. The object type whose retained size keeps growing across snapshots is the leak. I trace what's holding it. Almost always it's an unbounded cache or map, or event listeners that get added and never removed.
Good. Now tell me about the toughest bug you've solved.
We had a service that fell over roughly every 3 days. It turned out to be a database connection pool leak on an error path. When a query threw inside a transaction, the client never got released, so the pool slowly drained to nothing. I found it with heap snapshots over 2 days, a steadily growing array of pool clients, and traced it to a missing release in a catch block. I fixed it, wrapped the pattern in a helper that always releases, and added pool metrics and alerts.
Nice write-up. And how do you handle production incidents and pressure?
Preparation first, good monitoring, runbooks, a clear on-call rotation, so an incident isn't a surprise. When one hits, stop the bleeding before chasing root cause, roll back, scale out, or flip a feature flag, and keep stakeholders updated the whole time. Then once it's stable, do the real root cause work and a blameless postmortem with action items.
Okay, Ananya, that's everything from my side. Before we wrap, do you have any questions for me?
Yes, a couple. How's the team structured, and what's the biggest technical challenge you're facing right now?
It's a 6-person platform team, and the big push is breaking the legacy monolith into services without downtime. Exactly the kind of work we discussed.
That's great to hear. And what would success look like for this role in the first 90 days?
Owning one service end-to-end and shipping a meaningful improvement to it, reliability or performance. Great. Thanks for your time. We'll be in touch about next steps.